Calculus, video 40, examples of the derivative of inverse trig functions. So we now know the derivative of the inverse trig functions, specifically for the derivative of inverse sine of u, the derivative of inverse tangent u, and the derivative of inverse secant u. So let's go through about 5-6 different examples here. Starting with this one, the derivative of the inverse tangent of 3x squared, where the 3x squared is acting like our u. And we remember that the derivative for inverse tangent is u prime over 1 plus u squared. So, therefore, the answer here is u prime. What's the derivative of u? Right, our u here is the 3x squared. The derivative of 3x squared is 6x over 1 plus the u 3x squared squared. Or in other words, 6x over 1 plus 9x to the fourth. Done. The derivative of the inverse tangent of 3x squared is 6x over 1 plus 9x to the fourth. Okay, let's try another one. This time, number 2, let's go with the derivative of the inverse sine of 2 squared x. Okay, or maybe we'll rewrite this as the derivative of the inverse sine of 2x to the 1/2 power. Right, and that 1/2 power is just on the x, not on the 2. What we know is, for the inverse sine, the derivative is u prime over the square root 1 minus u squared. Again, we just need to know those. Okay, what is the derivative of 2x to the 1/2? So the derivative of 2x to the 1/2 will bring the 1/2 down. That's 1x to the negative 1/2 divided by the square root of 1 minus u squared. U squared would just be 2 squared, which is 4. X to the 1/2 squared is 1, so that would just be 4x. Which is a fine answer, but maybe we simplify it since we have a negative exponent in the numerator here as 1 over square root of x, square root of 1 minus 4x. That's it. All right, number 3. So while these are, seems kind of weird and complicated, once you get into the problems, they're actually not quite so bad, I think, anyway. It does take knowing those derivatives to make it not so bad. Let's take the derivative of the inverse secant of e to the x. Okay, so again, the e to the x is acting like the u value. For inverse secant, if you recall, it's u prime over the absolute value of u, square root u squared minus 1. Again, we just need to know that. So we get u prime, the derivative of e to the x, e to the x, divided by the absolute value of u, the absolute value of e to the x, times the square root of u squared, that's e to the x squared, e to the x squared minus 1. And let's see if this will simplify. Think about e to the x for a minute. E to the x, the graph looks like this. Turns out e to the x is always positive. It's always above the x-axis. So the absolute value of e to the x is still e to the x. E to the x over the absolute value of e to the x, which is e to the x. Square root of, let's rewrite this e to the x squared as e to the 2x. Right? You can multiply those exponents. E to the 2x minus 1. We see that the e to the x on top and the e to the x on bottom cancel out. There's still a 1 on top, so you get 1 over the square root e to the 2x minus 1. Very good. Number 4. Let's start with making it maybe a little more complicated here. How about the derivative of, let's go back to inverse sine, of cosine of x. The derivative of the inverse sine of the cosine of x. So our cosine of x is acting like the u. We know for inverse sine, it's u prime over square root 1 minus u squared. All right, let's try this out. Equals u prime, the derivative of cosine of x. That is negative sine of x over square root 1 minus u squared cosine squared of x. And that might seem like that's all you can do, but if we remember our trig functions, our trig identities, we remember that sine squared of x plus cosine squared of x is equal to 1. Or if you rearrange, sine squared of x is equal to move the cosine squared to the other side, or subtract cosine squared from the other side, 1 minus cosine squared of x. We see that 1 minus cosine squared of x is actually equal to sine squared of x. So, we get negative sine of x over the square root of 1 minus cosine squared of x, which is sine squared of x. That's negative sine of x over sine of x, which is negative 1. Possibly. More accurately, let me back up. More accurately, when you have the square root of sine squared, that creates something that's positive, right? If you take the sine of x and you square it, that makes positive, and the square root of that is still positive. So in actuality, we get this. It's this negative sine of x over the absolute value of the sine of x. And so this is that sort of 1, -1 thing, right, where it's kind of the sinum function we've called it before. Right, so either it's going to be 1, or it's going to be -1. Or it's undefined at 0, perhaps. So there's 0 here. If the sine of x is positive, right, so if the sine of x is positive, like in quadrant 1. In quadrant 1, the sine of x is positive. And the numerator, we get sine of x, that's positive, but there's a negative on the outside, so you get negative. And then the denominator is always positive, same value, and you end up with -1. But in quadrant 3, for example, when the sine of x is negative, the sine of x being negative is negative, but the negative out front becomes positive. Denominator always positive. You get positive over positive, which is +1, because it's the same value. So you end up with this, it's -1 between like 0 and pi, and then it's +1 between pi to 2 pi, and then it's back to -1, and you get something that kind of looks like this. It just keeps jumping back between 1 and -1, depending on which quadrant you are in. Okay. So the point is, we can't just cancel that out and make that -1, because it's not always -1. Sometimes it's +1, and so we just leave it negative sine of x over the absolute value of sine of x. That was a little tougher at the end there. How about number 5? The derivative of the inverse tangent of the natural log of x. I hope that you're pausing the video on each one of these and working them out yourselves. I haven't said that so far on this one, so maybe you are, maybe you're not. But if not, try it on this one. Pause the video, see if you can work this out. All right, so what I'd like to think of is that natural log of x is u. And so I know the derivative of inverse tangent is u prime over 1 plus u squared. So I get u prime, the natural log of x, the derivative is 1 over x, over 1 plus the natural log of x squared. On that natural log of x squared, there's a difference between the natural log of x, all in parentheses squared, and the natural log of x squared, where the square is on the x. If it's the bottom one, that 2 can come out in front of the logarithm. If it's the top one, it cannot. When it's the whole logarithm being squared, you cannot bring the 2 out front. So we're just going to leave it as the natural log of x in parentheses squared. The only thing we might be able to do is 1 over x becomes 1 over x times 1 plus natural log of x squared, like so. All right, bring that x down to the denominator. Okay, and finally, number 6, the derivative of, I think we did one inverse secant. Let's do another inverse secant. The derivative of the inverse secant of 1 over x, which maybe we will rewrite as the derivative of the inverse secant of x to the -1, just to make that derivative a little bit easier. That's not what I wanted to do. Not sure that 1 was any better. Anyway, the derivative of the inverse secant of x to the negative 1. So when we're doing the derivative of inverse secant, that is u prime over the absolute value of u, square root u squared minus 1. Okay, the u, in this case, is the x to the negative 1. So the derivative there, the derivative of x to the negative 1 is negative 1 x to the negative 2, that's the u prime, divided by u, so just x to the negative 1, but an absolute value, square root u squared x to the negative 1 squared minus 1. Let's see, so we get negative x to the negative 2 over the absolute value of x to the negative 1 times the square root of x to the negative 2 minus 1. Which I guess is a fine answer. Let's see if this simplifies at all. Let me start here. Inside the radical, the square root there, just maybe do a little side work. The square root of x to the negative 2 minus 1. Let's look at that as the square root of 1 over x squared minus 1. So that would be the square root of common denominators, 1 over x squared minus x squared over x squared, is the square root of 1 minus x squared over x squared, and the square root of x squared is the absolute value of x. Okay, so replacing this up here with that, I get negative x to the negative 2 over the absolute value of x to the negative 1, or maybe it's 1 over the absolute value of x. And then, down here, square root of 1 minus x squared over the absolute value of x. Square root of 1 minus x squared over the absolute value of x. Okay, now I have, in the denominator of the denominator, 1 over x in absolute value, and then another times absolute value of x. So that's the absolute value of x times the absolute value of x, which is the absolute value of x squared. But if you're squaring it, now it's positive on its own, and you no longer need the absolute values. So negative x to the negative 2 over the square root of 1 minus x squared over x squared, because that's now positive. No need for absolute values. Then we've got this, this numerator. Now I'll write that as negative 1 over x squared over square root 1 minus x squared over x squared. Think about this. Let's multiply top and bottom by x squared. That's just multiplying by 1. This x squared cancels out with that x squared, and this x squared cancels out with that x squared, and we end up with negative 1 over square root 1 minus x squared. Final answer. That simplification was a little tough, I agree, but it's good. It's a good problem. So we ended up with the derivative of the inverse secant of 1 over x being negative 1 over the square root of 1 minus x squared.